Mr. Carroll here with a question. How do you deal with series and parallel in the same circuit? Well, here's an example. This is from number 4, and it's one of the ones that I've asked you to try. And so you have two series resistors, then you have a parallel set, and then you have another series going back into our 12-volt power supply. And so we have to know the total resistance for the circuit. We have to know the total current for the circuit and total power, but there's a lot of stuff here. So what we're going to do is try to reduce this and then build it back out to find the specifics for each of your resistors. So the first thing that we're going to do is reduce numbers R3 and R4 into a single resistor, and we're going to label it R6. Now you notice R1, 2, 3, 4, and 5. R6 really doesn't exist, and so when we can't just leave it, we're going to deal with that later as we go through this process. So the process of dealing with a parallel circuit, 1 over R6 is equal to 1 over R1 plus 1 over R2 plus however many others are involved. Here, it's just going to be R3 and R4. So you look, it's 1 over R6 is 1 over 25 plus 1 over 50. 1 over R6 is, with the least common denominator, 4 out of 100 plus 2 out of 100. That gives us 6 out of 100. Then we flip them both over and we find it's 100 over 6. So my total resistance for this circuit, although it's a 25 and a 50, because it's in parallel, it actually is reduced to 16.67 ohms. Now we can then redraw this as a single resistor. Notice R6, 16.67 ohms, and now look what we have. We have a series circuit. A series circuit means that all I have to do is add them up. Now notice I have an R7. That means I'm going to get a single resistor that represents all 4 of these. R1, R2, R3, and R6. Actually, it's R5 here, but you get the point. 50 and 30, 16.67, and 75. So our total resistance is 171.67. So we get to put that out over here. Now, watch what happens. I have R7, 171.67, and now, because it's a single resistor, remember, your power supply only sees one resistance in a simple resistor circuit. So that's what the power supply sees. So from that, I can use V equals IR. I can calculate my current and find that it's 0.070 amps. Then I can do the same thing with the power. Power equals volts times current. So I take my 12 volts times my current, and I find my power for the entire circuit is 0.839 watts. Now I can't stop there. Now that's the total circuit, which is good, but I have to go back and find what's happening with each resistor. Now there are 5 resistors, and those 5 resistors we need to deal with. So we have to go back, but we can't go back to the first 5. We're going to go back to this series circuit because it's actually the simplest to work with. So remember, in a series circuit, the current is constant and the voltage drops. So this current is the same in R1, R2, R6, and R5. So you've already found 3 of them for what their current is. And so because we know that the voltage drop across R1, that's why it has a little 1 here, is equal to the current going through 1 times the resistance. So it's 0.070 times 50 ohms, and we find that the voltage is 3.5 volts. And just stick it right over here. I can now find the power, voltage times current, and guess what? That voltage that I just calculated goes right here, and my current is 0.070, excuse me, and I find it's 0.245 watts, and there's my power. Now that's calculating the first one. Well, guess what? The calculations for each of these is identical. You just go through the same procedure. The current is the same. The resistance changes, and that gives you a different voltage. The voltage goes down here times the current, and you get the power for each one. It looks like this. So resistor 2 has a different voltage and power consumption than resistor 5, which has a different power and voltage. and resistor 6. Now remember, resistor 6 is a combination of two other resistors that are in parallel, so we're going to have to keep a hold of that information. Otherwise, for resistor 1, 2, and 5, you are finished because the voltage and the power and the current has already been found. So we just have to go now and figure out how to deal with the voltage and the power and the current and so forth with resistors 3 and 4. And so I put 3 and 4 back up here, but notice your voltage and your power from 6, because this information is important because these two resistors are actually listed as number 6 on the previous slide. So now, because these are in parallel, voltage is constant and the current changes. So this voltage right here is constant. So because of that, I know the voltage across R3 and the voltage across R4 are exactly the same, 1.17 volts. So I list them right here. Because they are known, and I know my resistance, I can actually calculate the current that's going through each of my resistors. So I have 1.17 equals I3, the current going through resistor 3, times 25 ohms. And I calculate that as 0.0468 amps, that right there. Now, power, I take the voltage, 1.17, and the current, which I just calculated, and I find the power is 0.0548 watts. Now I do the exact same thing for the resistor number 4, and I place that information over here. Now you'll notice that the current between these two, if you add those up, it's the same as the total current in the circuit, because the current coming in and the current coming out of that parallel system has to be the same. The power, though, is not. Although if you add this and this, you get the power associated with what we did before. Now I know that's fairly complex and there's a lot of moving pieces in this, but you can rewind and come back through and rewind and pause and see if this is helpful to you.